So you're X-raying a component, but you're wondering, how much radiation are the neighboring components getting? Let's find out. So we've got an interesting question from the interwebs. Here's the question. Say there are 20 components that need to be X-rayed on a PCB. While X-raying the PCB, is the rads or the exposure the same for all 20 components when the X-ray is on, cumulative, or does the rads exposure change based on how far the component is away from the focal point? And if so, how do you account for this in the rads exposure calculations? Okay, that's a very good question, right? And the best way to understand and how to address this question is to think of the inverse square law. The inverse square law tells us that radiation drops as the inverse square of the distance between the spot size or the target location and the sample, right? So let's do a quick example here to understand and to answer this his question, right? This is the X-ray source, and again, what you see on a reflective source is the window, right? The target is somewhere inside the window, maybe 10, 11, 13, 17 millimeters inside. In a transmissive source, on an open source, the target's going to be right there at the window, but let's say, so take that in consideration when doing this math, right? So here's the target, and the X-rays are hitting, because you were imaging this component here, let's say component 1, and let's say this distance here is 3 inches. And then let's address the question by placing another component. Let's call it component 2. It's going to be right here. And component 2 is going to be 4 inches from component 1. So this is 4 inches, right? So 3 inches from the target to component 1, 4 inches from component 1 to component 2. Based on time, power, and distance, right? So those are the 3 things we need to know to calculate the exposure of this component. Based on time, power, and distance, let's say that I know that the exposure on this component 1 is 10 rad. So what's going to be the exposure on component 2? So let's figure this out. 3, 4, 5, right? We know the distance between component, the target here and component 2 is going to be 5 inches. 3, 4, 5, that's the simple triangle. The difference between component 1 to the target and component 2 to the target is 5 divided by 3, right? So the component 2 is 1.6 times farther away from component 2 than component 1 than the other component 2 is. So using the simple 1 over r square, you have 1 over 1.6, right, square. And 1.6 comes from 5 divided by 3. This relationship, it's about 1.6. So 1.6 squared is approximately 3. So this is 1/3. That means that component 2 is going to get 1/3 of the radiation that component 1 is getting, which means that component 2 is going to be about 3 rad. And that's how we go from moving 4 inches from the principal beam line, of course, assuming that you have a proper illumination across, we're going to consider that's going to be fixed. You're going to have about 1/3 of the radiation, 1/3 of the exposure that component 1 gets. Pretty straightforward, and that's a function, and that tells you how powerful the inverse square law is when calculating exposure of electronic components. If that is really not enough and you need extra shielding for component 2, if component 2, for example, is not being imaged at the same point, you want to minimize the amount of exposure that component 2 is going to get, you can always add shielding. Just put a plate here that blocks radiation from going to all the other components except component 1, which is the one you are trying to image. And by doing that, this exposure drops tremendously. You can basically get all the way to very close to background radiation. So I hope this was helpful. If you have any other questions like this one from the interwebs, feel free to reach out to us at info@creativeelectron.com. Go visit our website at creativeelectron.com, and do not forget to subscribe. Thanks for watching.